So this is the second inauguration talk, but still, I would argue that Lucjan is inaugurating the inauguration talks for tenured track faculties that got tenured. So that's really a first. So thank you, Lucjan, and we are all very glad to have you here. So yeah, so Lucjan started his PhD back in 2011, and I need my cheat sheet for the name of his advisor, which I'm going to utterly destroy, sorry. So Miroslav Kutilovsky is here in the room, so thank you for being with us, and that's really great. So after his PhD, I'm not going to give you the title, you can look it up, and it's written down on my cheat sheet, but I have forgotten anyway. It's about identification, document, crypto, protocol, something, but whatever. So after this, Lucjan joined the CISPA Stanford program, and he also went to sunny America and enjoy the place there. But after a while, he decided that it's probably time to come back to Europe. And you know what? He started at CISPA in 2020, around the same time as I did, and we both had this great idea of starting in this place at the moment where COVID struck. So that was really a cool idea to have, but yeah, But still, after 5 years, Lucjan had ticked all the boxes, and he got tenured, and we are so glad to have him here and to give his talk on, hiding secrets from whomever, I don't know, but we are going to see that. Thank you.
So thank you, Antoine, for the nice introduction. I would also like to thank all the CISPA organizers that make this event happen, and also thank to Michael for setting the bar too high for me now. Okay, so today I would like to talk about privacy-preserving authentication. I will come back to this later, but to give you some idea about the structure of the talk, I will first introduce myself, similar to Michael. Position my research somewhere at CISPA and what I'm actually doing. Then I will try to talk about 2 case studies, right? So I will dive not that deep into 2 papers, which I think are the most interesting ones that I did while being at CISPA. And finally, I will talk about some future work. So I will give some short-term and long-term ideas that I would like to explore, right? So background already mentioned. One thing that is not on this slide is that in a small time in between 2016 and 17, before I started being a postdoc at CISPA, there was a short phase where I was a research assistant at the university where I studied. And this will come back later, right? So just keep this in mind. All right. So what about my research? So I'm part of research area 1. Of course, cryptography is part of research area 1, but more than the basic and high-level cryptography, what I'm interested in is applied cryptography. So what I would like to think about applied cryptography is that I formally, this is important, mathematically formally define, specify, construct cryptographic schemes, protocols, that are used in practice or have some practical applications, right? So it's not really deep theory like Nico or Willy. It's more on the lighter side, closer to security. Okay. And what I also like to do, and you will see one example of this, I like to develop attacks, right? That are not the kind of attacks that you might think what Michael Schwarz is doing, but more of attacks that target the scheme, right? So I'm looking and try to find some bugs in the security definitions, the models, and maybe the crypto that is used, right? Okay, so I mentioned privacy-preserving authentication in the beginning. So what is privacy-preserving authentication? It's one part of applied crypto, and I would like to talk about this part of my research in this presentation. So this is why I want to also go into details about the specific names, right? So what does authentication mean? So authentication is very simple, right? You have Alice, and Alice wants to prove to Bob that she is Alice. And I added this part because this definition is from the Fiat-Shamir paper, but I added this blue thing, and that Alice proves some attributes about herself to Bob. So for example, it can prove that she's over 18 years old. Her surname is Hanzlik, for example. But the important part in authentication is that no one else can convince Bob that he is Alice, right? And you're using authentication every day when you log into your Gmail account. You're proving, okay, this is I am who I am, and please let me in, right? So Gmail let me in. So this is authentication. So now let's go to the more interesting part. What does privacy preserving mean? It depends, right? So it depends how you define it. As usual in cryptography, we have to define stuff, right? So we have to somehow formulate it. So I presented 4 privacy concepts that are somewhat related to my work, and I structured them in a specific way. So we have 2 that I will touch more about, those ones in blue, and then we have selective disclosure that is part of the future work idea that I will also target. So to just give you some hints about those privacy concepts, so one idea is this anonymity set, right? When you authenticate, you could, for example, prove to Bob that you are Alice, but you could also prove to Bob that you are an employee of CISPA, right? And then you have like a bigger anonymity set. You're not proving I am Alice, but I am one of CISPA members. And this is something that in cryptography we use with ring signatures or group signatures, and this is work that I did very early before even as part of the CISPA Stanford program. Okay, now we have 2 other concepts. So domain unlinkability is very important, and probably you heard about this. So it's a way to prevent different services from linking your ID. So imagine you don't want your health insurance to see that you are buying alcohol, right? Because then it might increase your health rate or something. So you want this kind of separation. You also want your private life to be separated from your work life. So this is domain unlinkability. Then we have blindness. Blindness is just a concept where you create a digital signature or a certificate without actually seeing the content of this message or the certificate that you signed. We will come back to this later. And finally, selective disclosure. It's something that has to do with identity management, where you actually want to only reveal the information that is necessary, right? So like going back to the Alice Bob case, so when Alice is proving that she's over 18 years old, she doesn't necessarily need to prove that she's a German citizen and her surname is Hanzlik, right? So you don't have to do this. So you only want to selectively pick which data you want to reveal to the one party that you are authenticating to. Okay, so those were nice concepts, but why does it matter, right? So why do we actually care about privacy? So there are plenty of reasons. So I picked this infographic kind of thing. So browsing habits can influence your credit score. You can get targeted ads, health insurance data. Like health data might increase your insurance pricing. Your social behavior might influence your employee decision, and so on, right? So there are a lot of reasons why we should have privacy. And of course, where does crypto fail, right? Because like I need to talk about something, so I need to talk about some kind of problems here. And where does crypto fail short? So I prepared those 3 points, and they nicely align with the next steps. So in the first point is that provable secure crypto doesn't mean that you have that all is nice, because it actually depends how you use it, right? So that's one thing. The other thing is like sometimes what we cryptographers think is the right model is not actually the right model in the real world, okay? So sometimes we think about it too strong. And finally, I think this is the most important part, is that in most cases, we don't really care about privacy that much, and we just say, okay, let's just do usability, performance, compatibility with older devices, and forget about privacy, right? This is we try to have this kind of trade-off where we push more on those other points than on privacy. Okay, so now I will actually show you what I meant by this first point, right? So where using crypto in a bad way might leak some information, and this is based on one of my papers, how to not handle keys, where we actually broke some privacy guarantees in FIDO, where I will talk about what FIDO is in the next slides. But to give you some backstory, right? So how does this work came to happen is it's an Australian story, actually, funny enough. So Michał Kępkowski, in 2020, he contacted me and told me that, okay, now he's a PhD student in Australia with Dali Kafar, and maybe you want to do something with me, right? So I knew Michał because of this short period that I mentioned, right? When I was a research assistant at my alma mater university, I actually was teaching him a course on smart cards. So he remembered me and he contacted me and said, hey, let's do something together, right? So and I guess this was a nice story, because the result was actually 2 papers and 1 exchange grant, where Michał came to Germany and one of my students went to Dali Kafar's group in Australia. Okay. So I mentioned Michał contacted me and he told me, okay, let's do something about FIDO, because he was interested in FIDO. So what is FIDO, right? This is the big name in the room. What is FIDO? So FIDO is just a standard for authentication. So usually, you probably still use login passwords, so that's your way of authenticating. But if you want to do something better, you could move to public key crypto. And FIDO is just a fancy name for using public key cryptography in a standardized way. And it's composed of some 2 protocols. You have this web authentication, which basically defines the communication between your browser and the server, so your website, let's say. And then you have this client to authenticator setup protocol, right? And I'm mentioning those roaming authenticators or platform authenticators. Maybe you saw something like this small USB stick. Maybe you recognize the name Yubico, YubiKeys, kind of things. Those are external devices. They are storing a secret key, and they can be used to log into your accounts, right? And of course, with the following instances of this FIDO standard, we also have something called passkeys. So you can even use now your phone as a way to log into your accounts, right? All right, and to just give you some hints, it's supported. The standard is very supported by big tech and also by, for example, BSI in Germany, right? Okay, so how can you use this, right? So how can you use FIDO? So it's pretty similar to what you do currently. You have a registration and an authentication phase. So currently, when you register, you have to fill out all your names, stuff, email address, and your password, right? In case of FIDO, you do the same, but instead of filling out your login and password, you just use your token, and you're sending some kind of credential to the server. And this credential, you can think about a public key in cryptographic sense. When you authenticate, so when you are trying to get access to your account, you get a list of credentials that are bound to your account, and also a challenge. And this challenge is just signed by your device, and this signature is the way that you authenticate. So the signature is just a digital signature that this small device creates over the challenge. So one thing that I want to highlight here is that you get a list of credential IDs, because your account can actually have multiple tokens registered, right? So you can have like 5 tokens, and the server doesn't know which one you are currently using, so it has to send all those IDs, and you just pick one that works. Okay, so there is one big problem with this technology, because okay, we are talking about privacy, but if you everywhere you use the same public key, that would basically mean similar to using the same email account everywhere. So, and you probably heard this, that you should use like different email accounts if you want this domain separation, right? But here we would be using the same public key, so we also have like a link between those accounts. And to get rid of these accounts, the idea is to just use separate public keys. So for each new service, so for example, if you go to Google, you have one public key. If you go for Yahoo, you have another one. And the problem is that those devices, those small devices, they have limited secure memory. So how would you store this information about the secret key? You just encrypt it, and you send the encryption to the server. All right? So that's the idea. And with that, when you authenticate, you get the ciphertext back, you decrypt your secret key, and you can authenticate. Okay, so far so good. So it solved this limited secure memory problem, because you have just one master secret key on your device. So we investigated this with Michał, because we found some information how Yubico is doing this. So we found out that they have one master secret key, and they also include the name of the service that you are using into this ciphertext. So it basically means that when you get from the server, you get your ciphertext, you decrypt it, you check, okay, does it correspond to Google? Yes, I'm connecting to Google, so I can use the secret key. And this was already concerning, because we were thinking, okay, so if this is how it works, maybe there is something we can actually do here. So to take a look at the actual code that Yubico has is not possible, because Yubico has a closed system. So we did the next best thing. So we found out this OpenSK project, which is Google's way of implementing those FIDO tokens on some hardware, right? So they have like this open source project. And then we took a look at how they're doing, right? So I highlighted 3 steps. So like in the first step, you have correctness of ciphertext, which is basically checking whether this ciphertext was modified. In the second line, you do decryption, and in the third line, you do checking if the key is correct, right? So if the key is for the correct service. So what does it basically mean? That there is a time difference for the following case. If assume this is the code run by Alice's device, if you get as input a ciphertext created by Alice's device, it will follow, and it will abort potentially on step 3 only. Because if you send a ciphertext of Alice, but for a different service that you are currently communicating with, it will pass the first check, it will decrypt, and it will fail on the third step. But if I'm sending a ciphertext for Bob, it will immediately fail on the first step, because it will recognize this is not an authenticated ciphertext by Alice. Okay, so we found that, okay, maybe there is something going on here, right? So we took some authenticators. Actually, we tested 8, and 2 had the following problem. If you have a ciphertext of Alice, but for a different service, so you try to log into Google, but you're sending Alice a ciphertext for Yahoo, it will take 49 seconds. But let's say you send a ciphertext of Bob to Alice's device, it will work just 39 seconds, right? So 10 milliseconds difference. Of course, so now since we have this timing difference, we would like to exploit it, right? So what we did is we took a look at this scenario where you have one service and then you have a malicious service. The user registers with the credential Alice in one of the service, with credential Bob in the second one. Then somehow by maybe database breaches or maybe by collusion, the malicious service learns that Alice's credential in the first service is credential ID 1. And now the goal of the adversary is to say, okay, is Alice and Bob the same person, right? And they can actually do it, right? So what we did is we just sending this credential ID followed by the correct credential ID. So remember, we had a list of credentials, and we measured the time. Of course, 10 milliseconds is not that big for network delay, so we actually boosted this up, right? So you could just duplicate this one credential, and it boosted to even a couple of seconds, which is already noticeable to a remote adversary. Okay, so that's it for the technical part. So now you can relieve. So now about the results, right? So the results were actually quite nice. We reported this issue with the manufacturers. They didn't reply to us. That was interesting. But we also reported those to all browsers, right? So like Firefox, Chrome, and the Chromium team was the only one that replied to us. But the funny part here is that it's not a browser problem. It's actually the problem of the token, right? So of this hardware device. Those manufacturers used crypto in a wrong way, but of course the Chromium team accepted, okay, it might be also a problem because on our part, because we accept duplicates, right? Or a big list. So after we reported this, what they changed is now that this big list that could have like 50 or 100 entries, now it's limited to, I think, 10 or 15, and you can also not have duplicate entries in the list. And the nice thing was that the student got a bug bounty, which is easier to get in Australia than here at CISPA, I guess. Formally, I mean, formally, not getting it. And the follow-up also was interesting, that the unlinkability definition. Okay, so once we had this attack, we were thinking, okay, nobody was considering this kind of attack. So like in the actual formalizations of FIDO from a cryptographic perspective. So we actually introduced this, and this was work with Julian that we did on unlinkability in FIDO. Okay. So that was the first point, right? So what I showed you is that if you use crypto that is still provable secure, right? They use authenticated encryption, which is a well-defined and secure primitive, but they used it in a way that still leaked information and broke privacy, right? So I showed you that like you have to use crypto in a very specific way to make the whole system secure. So now I want to move to another example. That what I want to show you now is that sometimes we cryptographers have too strong of a model for the actual problem, right? So there are problems where we think, okay, let's use a big hammer for a small nail, right? We just need a small hammer for the small nail, but we use a big hammer. We just slap the best crypto we know, the best formulation, and we go with it. So now I want to show you that maybe it sometimes makes sense to think about this and rethink what we really need. Okay? So remember, I was talking about one of this privacy concept, which was called blindness. And blindness is just a way of saying it's one of the properties that a cryptographic primitive called blind signatures have. So you might know about digital signatures, which are just signatures using electronic devices, right? Like they use this fancy crypto to sign electronic documents. But you always, when you envision this, it's always the signer always knows the message, so he basically knows, okay, this is the PDF file that I have to click to get travel done, right? You click it on the bottom, and now it's signed. In the case of blind signatures, it's a bit different, right? We have this interaction between the signer, who owns the key, and the user. And during this interaction, the user receives the signature under the message, while the signer doesn't learn anything. And the real-world analogy here could be, for example, a notary seeing a document, right? You go to the notary, you show him a document, he doesn't see the content, right? Because this might be some information that you don't want to leak to him, but he's signing at the bottom that he saw some kind of form of a document, right? Okay, and where are those blind signatures useful, right? Or where is this concept of blindness useful? So there are many old examples where blind signatures are used, but I wanted to show you one of the recent ones, right? Where it's actually where actually blind signatures are used in a deployed system, and this deployed system called privacy pass solves the following problem. So you probably saw it by yourself when you use Tor network, or if you use a VPN like Mulwat, you know that you are more likely to be queried by CAPTCHAs, right? So like if you browse the internet, it just pops you click here, right? Is this a bus? Is this a hydrant or whatever, right? And that's the problem that Cloudflare tried to solve. That they still want the bot protection, right? They don't want bots in their system, but they don't want to actually limit the usability for users, right? They don't want to force users to solve CAPTCHAs every time. So an idea to solve this is actually privacy pass. So in this privacy pass system, what you do is, as a user, you first download some browser extension, and using this browser extension, you can go to Cloudflare. Cloudflare now becomes your issuer or your signer, and during this interaction, you first solve a CAPTCHA, or you can use device attestation. So for example, I'm talking here about Cloudflare, but Apple has its own version of this privacy pass system, and in their system, you are not solving CAPTCHAs, but you're actually using your device, basically. So while using a genuine Apple device, you can prove to the issuer that you are not a bot, right? Okay, so once you're done with proving, attesting that you are who you are, you get this kind of coupon as a result, right? So when Bob has his browser, he gets coupons. And now, of course, if you have coupons, you have to spend them, right? So how do you spend them? You use your pick of anonymous network, either Tor or VPN, and instead of solving the CAPTCHA, like the service provider would ask you, okay, please solve the CAPTCHA, it also can ask you, please give me a coupon instead. And you are just spending coupons, right? Of course, we don't want to give out coupons for free, so the idea is that you give a limited number of coupons every time, so like 20, 30 coupons every time you do this first phase. And what's most important for privacy reasons, of course, because in the upper interaction, right, Cloudflare knows that Bob is Bob, right? It either sees his device identifier, it knows, okay, you are using an iOS, Apple, iPhone, while what Bob wants is he wants to hide whenever he goes to the service provider to look up his favorite website, he wants to hide his identity, right? He wants privacy. So we want those two processes to be unlinkable, basically. And if we ensure that this is unlinkable, we get this nice privacy guarantees like domain unlinkability, blindness, and whatnot, right? So we get a lot of those privacy guarantees from this. Okay, so when I was thinking about this, right, about this privacy pass system, and I just want to mention that this privacy pass system is actually an implementation of what is called Chaum's eCache. David Chaum is one of the early days cryptographers. He developed a digital cache system, but unfortunately it didn't catch. And now we have cryptocurrencies, which is an extended, better version of that because it solves double spending and whatnot. But anyway, so this privacy pass is just an instance of this Chaum's eCache system. And there are a lot of other instances, but I wanted to mention privacy pass. But why is this interesting is that in most of those systems, this coupon or this eCache is just a signature under a random serial number, right? So it's not a specific message. It's not like Lucjan Hanzlik and a signature under Lucjan Hanzlik. It's just a random string of numbers, right? So like a random number, serial number, and then a signature. And this forms your coupon. So your coupon is a kind of signature under some random data. So when I was thinking about this in that term, I noticed that in all those formalizations for blind signatures, we just assume, okay, the message is always picked by the user, right? It's never some random stuff. It's always picked by the user. Of course, with this, you can construct it, because if it's picked by the user can just pick a random value. But maybe we can do something more if we assume that it's outside of the user's power to pick the message. But at the end, he still gets a coupon, right? And with that idea in mind, I developed the concept of non-interactive blind signatures. So you remember blind signatures, we had this interactive way of issuing signatures. Now we have a bit of a modified version where Bob has a public key, which is known to the service provider, right? So to the issuer. And what the issuer can do, the signer, he can send this something that is called a pre-coupon. It's useless to anyone because it's just some piece of cryptographic data, unless you have the secret key of Bob. Once you have the secret key of Bob, you can finalize your coupon. And now you have a coupon. Of course, you didn't pick the message because it's a random function of your secret key, but it's a valid coupon. And you still have this blindness property because the one creating the pre-coupon doesn't learn the actual values that you will get in your coupon. All right? So, okay, this was the concept idea, but how can you apply it to this privacy pass case, right? So remember, what we want from this privacy pass system is that you get coupons, and later you can spend them when you're browsing the internet, right? So imagine now that Bob just registers once, right? Let's say he registers on the weekend, right? And then on Monday he receives 3 pre-coupons. So those are not finalized coupons. On Tuesday he receives 1 coupon, and he doesn't even have to be active or online on Monday or Tuesday. He can just go to Cloudflare on Wednesday and download those coupons. So there is no interaction required. And this idea allows us to, for example, use idle time computation, right? Which is one of the interesting things in computer science. Like, a lot of servers are just idling down. They're not doing anything during low computation, right? Times where like not a lot of people are using the services. We have a lot of free time where we could actually use this time for creating those kind of coupons, right? So there are also other applications, right? So what we could do with this non-interactive blind signature is airdropping coins. So I don't know if you heard about cryptocurrencies sometimes get this airdropping, right? So imagine that you are an inventor of cryptocurrency, and yeah, you developed your new fancy cryptocurrency, and now you want to have users to use it, right? You want users to use it, but you don't have actual users. So what you do is you just pick random users from the internet, like by looking up their public keys, and you can just drop them some coins for free, right? You're just dropping them money for free, and they can use your cryptocurrency. And you can do the same thing here, right? You could airdrop coupons. You just need Bob's public key. And one application that, when I was writing this paper, I had in mind was a whistleblowing system. I don't know if you know, like, if you have a company over 250 people in Europe, you need a whistleblowing system, right? We also have one at CISPA, but I guess nobody knows about it. Because we just use some open software that probably has a lot of bugs. Anyway, whistleblowing. So the idea that I was envisioning is maybe when you are connecting to any of the services at CISPA, you get a pre-coupon for free, right? You can either drop it to def null, or you can finalize it and then use it to spend as this whistleblowing system, right? With this, we basically create a big anonymity set. Remember, anonymity set meant you want to hide your identity amongst all CISPA faculty, or not faculty, but all CISPA members, right? With this system, we know that everyone received a pre-coupon, so everyone could be a potential, like, one of the whistleblowers, right? Of course, here it's maybe whistleblowing sounds in a negative term, but it's actually a good thing, right? So, like, if there are some something going on, we should have this kind of system. And with this, you could ensure that you cannot actually decide who was the one reporting, because everyone at CISPA would be the same potential suspect, right, in this case. All right, so those were the applications of non-detectable blind signatures, and just to mention that there were a lot of follow-up works, and this sparked a new direction in those blind signatures, a lot of follow-up work by my group and by others. All right, so now talking about short-term research plan, I want to highlight and talk about what I plan to do in the next maybe 2-3 years, and then talk about some long-term plans. So European digital identity. What is the European digital identity wallet? You maybe heard about this. We have to have it until end of 2026. I don't know what is the current state, but each state member, so like all EU members, have to deliver. We need this kind of app. What is this app? So you probably used your mobile iOS wallet or Android wallet for storing your plane tickets, what other tickets. Imagine you have the same thing, but for your diplomas, for your identity card, for your driving license. So imagine this kind of super app. It's doing everything, and it also has a feature for this selective disclosure that I mentioned, right? So now you want to prove to someone that you are over 18 years old, but not show your name of any other stuff. So with this, you should be able to do it, right? That's the underlying idea, and this is something we should be getting until end of 2026. All right. So what is the basic like outline here in the system, right? We would have three actors: the issuer, the holder, and the verifier. Of course, basically the holder can request some credentials. Say you go to the university, you say, please give me a credential that I am a PhD student, or I'm a PhD student, or I have a PhD degree. You get the credential, and maybe CISPA will be starting issuing certificates for tenured faculty, so we could have them in our EUD wallets. And then when the time comes and you want to go to a verifier, you want to access some maybe age-restricted service or something, you can present your proof, right? And as I mentioned, the whole point of this EUD wallet is to give power to the user. So the user should be the one deciding what you want to show. So for example, if the verifier asks, please show me age and name, and you just show age, maybe you will not get access, but it's up to you to decide what you want to show, right? So it's self-sovereignty of your identity. This is the whole concept of the EUD wallet. All right, so this is roughly how it looks like, but of course there are no problems, right? So like the first solution is just take something that is already implemented. This MDL, which is the mobile driving license, for example, in Australia, is implemented. Just take whatever they did, and now we are good to go, right? Unfortunately, that's not true. There was this huge review of this technology by cryptographers, and they noticed, or they mentioned, two main things. Is, for example, the issuer can track the holder, meaning that if the issuer, it could be a state government, but it also could be a big tech from outside the EU, and then they can basically track you everywhere. So they can see all your where are you going, right? If they somehow cooperate, of course, with the service provider, but that's not that of a problem for big tech like Google or others, right? Where they could have access to those things. The second problem is also that those credentials are single use. So if you show your age once at the local shop, and then you show it in another shop, they can tell, okay, this was the same person. So you would basically need to, if you want to really have full privacy, you would have to get a new credential every time to show your age, for example, right? Those are two big problems. So of course, as as crypto people are known for, we just took the strongest solution, or maybe the best solution we can think of, right? And the current state is that we have two solutions. One that is the basic one, that has all those problems. One that is super advanced. It has solved all the problems, right? And it relies on zero knowledge proofs, and it's far behind in standardization. So the one problem of this advanced solution that the cryptographers proposed is it's not standardized. It doesn't work with all the hardware that we have out there. So it will probably not be implemented, and probably it might take 10 to 15, maybe more years to make it done. So we just opt for the first solution, right? And the second one is just for experimenting and pilots. So that's the current state. So of course I'm not happy with the current state, right? So my short-term plan is to try to have like a transition phase, right? We have this basic solution, we have this advanced solution, but there is nothing in between, right? So we either go for some privacy and linkability, or we go for full, which doesn't work or will not be implemented. So maybe we can do something more with cryptography and some nitbits of system security, right? So I want to actually look at this part. So I want to look at the issuer and holder part. So my idea is here that the wallet app that you implement, it has to at least support this basic version. But nobody says that you can't have an extension, right? So imagine that you are a company that is acting as an issuer. It says, here, download my app. You can use it with anyone. You can get credentials from Unisarland. Then you use the basic version. But if you use this app with me, you get extra privacy, right? You get extra stuff for free because I'm good, right? So what I was thinking about is maybe have some kind of extension that underneath is still all compatible with the existing system. It's just an add-on that will tell the user, if the user is conscious about this, they can pick the solution that provides more privacy to them. And the issuer can actually give cryptographic guarantees that, okay, I'm issuing you the credentials according to the weak standard, but I can give you guarantees that I don't know and I cannot track you, right? So this kind of guarantees we can make it happen with crypto and some system security, right? And I want to explore this direction more. Okay, and to just give you some intuition how I want to achieve this, right? So like I have this, or I've written those ideas as part of some work packages in a Horizon project, which might lead to one PhD and some Hiwi positions for implementation, which I find interesting. I also have an ongoing project on a similar problem where what happens if you run your application, this wallet application, in a hostile environment, right? By hostile environment, I mean maybe your smartphone has some kind of malware installed, or there are some actors that might behave dishonest and all those kind of problems. Okay, and finally, I think this is something I also mentioned during the faculty retreat. So I really would like, if I have all those nice results, I would really like to have some kind of open source, maybe CISPA wallet or something like this, right? So I think this would be really, really great. And I mean, some people are interested in EUD wallets and in this kind of technology, so maybe we could make it happen, right? Okay, and finally, just a short a teaser about my long-term plan. So I want to work on something that I call, I don't know whether the name makes sense, practical cryptography, right? So practical cryptography, what does it mean? It's basically, I want to look at existing systems and check, okay, what are the properties that you want? Or like what properties do you really need from the crypto? And then maybe look at the formalizations of those cryptographic primitives, change them to what actually is needed, so downgrade them a bit, and maybe by downgrading we can get something out of this, so some new kind of properties, similar to what I did with those non-interactive blind signatures, right? So, yeah. I just want to briefly go back to those three key takeaways that I want you to remember. Is one thing, right? You have to use cryptography in a way that actually is correct, and because you might end up with privacy leaks. The second thing is, like, maybe we are sometimes trying our best while constructing all those super secure systems, but maybe it sometimes is not really needed. Maybe we can do something smaller, and then we get some new properties out of this. And finally, we also should think about this trade-off, right? So maybe we shouldn't be trying to go full max on usability and performance. Maybe we also should think about privacy, and this is what I want to do in this short-term plan, where I want to really have this kind of transition phase, right? So it's like a smoother transition from just one weak solution that is compatible, usable, to something that's stronger, right? Okay, so thank you, and I guess we for the time I think questions were.
We have a little bit.
Okay, so let's go. Okay, let's do a couple questions. That was.